helping us. Like even if I just had a picture of the function itself, it's kind of hard to see a saddle sometimes. But here, it's obvious what's going on with the function, right? Because you can just see that the gradient is increasing this way, and the function is decreasing that way. You can just see it if you look at the gradient vector field, right? So with the gradient vector field, we can analyze the behavior of a function very, very elegantly. So here, I just have more pictures. Here's your line. Here's the line one you wanted. Although I don't have the vector field, but the gradient vector field would just be what? Like this, like this, like this. Here's the graph. Which has more information, the graph or the contour plot?
Well, if you know how to read the contour plot. Yeah.
Right. If you know how to read the contour plot, I would argue the contour plot has more information, despite the fact that it's not as cool looking. I think that's kind of something you can take away from this is that, there's an advantage. I mean, this geometrically, of course, gives you a better sense of what the graph looks like, right? But if you're actually interested in specific analytical details and you have a nice contour plot like this, you can actually get more information from it. Depending on the preparation of the graph, right? This is more like what kind of graph are these called? For like, what is it? Topographical, right? So the topographical. Topographical maps are like contour plots. Yeah. So here's another picture of that xy function, I think. Oh no, this is a different one, but it's the same thing, right? By the way, you can see that this is the same as the xy function, can't you, geometrically? Like the xy function, it goes down one way, it goes up another way, it's a saddle. This goes, see, I can't even see from this stupid thing. It's hard for me. I don't know. I mean, you got to be able to rotate these things to really see what's going on, right? That's the nice thing. And in the computer algebra systems we have do allow for that. But, all right, so I want to get this out of my system here today. Oh, look at this one. All right, I will not be distracted by this. I will not be distracted by this. Oh, look at, what's this? Look at this function. It's got all these kinds of interesting wiggles in it. Wow, that's really interesting. No, this is just Maple failing. Well, it's not so much Maple as my computer, right? You see something like this in your graph. What should you understand from this?
That you're either looking at like a surveying map or that you're about to die.
You're about to die? You're getting near the event horizon? Yeah, I don't know, whatever. No, this is just insufficient sampling, right? You're picking up discontinuities that are a signature of the calculation, not actually the graph. So one of the reasons you're taking this course, right? You're like, well, I can take partial derivatives. I don't need to take partial derivatives. I can do that in Wolfram alpha, right? But the thing Wolfram alpha can't do, right, and never will be able to entirely, is to understand that this is just a machine's failing. That's where you guys come into play. That's the difference between being a technician and being an engineer also. Understanding, right? So that is our higher goal here. I mean, yes, computation, you have to compute things in order to understand, all right? That is true. But that's just the first step, right? All right, again, here's the three-dimensional partial differentiation. I'm not going to belabor it. What I want to get to here is, oh, for one thing, if I can find my example. Just a second here, guys. Where's that stupid thing? Did I keep it? Yeah, let's look at this question for just a second. This one's kind of awful. Suppose you have a function of 3 variables. Well, that's a reasonably nice function, though. Does f increase at a rate of 2 in any direction at the point 1, 1, 1? Calculate a gradient vector field, 2, 1, 2. That's easy enough to evaluate at 1, 1, 1. It's still 2, 1, 2. All right. So when you have a constant vector field, evaluation is really hard to mess up. People will find a way. People will find a way. But you shouldn't find a way. Anyway, so the magnitude of this is root 9, which is 3. So that's the maximum rate possible. So yes, we will find directions in which the rate of the change of the function is 2. So we're basically looking for this dot product to be 2 and subject to the condition that a squared plus b squared plus c squared equal to 1. In other words, in three-dimensional problems, the unit vector is a point on the two-dimensional sphere, right? And so there's a whole sphere of directions that you got to choose from, right? It's not that that's not that AB space anymore. It's ABC space. So I got to solve this with respect to that. So I guess what I did was I solved for C and plugged it in here, and that gives me that, right? That gives us an ellipse in AB space. Every point on that ellipse is a solution. There are infinitely many answers. There's infinitely many directions in which we can change at the rate of 2. Yes. For example, we can easily solve the ellipse equation for its b-intercepts by putting a equal to 0. So like these. So I either get 0, 0, and 0, 4, 5 on the ellipse. And then going back to C, it gives me C equals to 1 or C equals to 3/5. So I get direction vector 0, 0, 1 or 0, 4/5, 3/5. So you can easily go back and see that the dot product of these unit vectors with our original gradient vector gives me 2. But these are just 2 in a whole infinity of answers. Yeah. So this is what I was telling you about yesterday, Thomas. So you're like, you could just find the theta to figure out, and that's true. Like Thomas was saying yesterday, like as opposed to doing the a comma b calculation we were doing, he would think about a theta, because Thomas thinks very geometrically, right? So he thinks about how to find the theta between the given unit vector, between the gradient vector direction and the unit vector I want. You know, I choose a theta to make that length of the gradient vector times cosine theta equal to whatever rate I want. And he just works geometrically from that point, as opposed to finding the intersection of the line and the circle in AB space like I taught you yesterday. Well, I tried to teach you. But as you can see, that's why I was telling you, Thomas, like in 3 dimensions, we're out of luck, because then we got this whole infinity of answers. I'm sure you could still find some geometry for it.
I'm sure that if you think about the given space as a hyperplane, if you will, then with if you have 2 angles, theta and phi, you're probably be able to.
Yeah, I think so. I'm much more algebraically inclined, right? And so, in my experience, there's a larger portion of students who are able to grasp the algebraic approach, and there's a small subset of you who are really geometrically inclined. So I don't teach.
I'm not terrible at algebra, so I can do it the other way.
Right.
But
The thing about algebra is we can always do algebra, even when geometry is fine. I don't disagree. Okay, so I wanted to finish today with the 3-dimensional story, 3-dimensional version of the 2-dimensional thing I was doing, all right? Because tomorrow I'll be talking about the tangent plane that we started to talk about today, all right? Anyway, so here it is. If f is differentiable, we can define a gradient. And so here, a subset of Rn. So you can just as well assign an n vector and have an n-dimensional vector field. For example, in 3 dimensions, the gradient of a function of 3 variables gives you a vector field in 3 dimensions. One at each point as a function. At each point, it describes the change in the function there. All right? Simple example, x, y, z viewed as functions of 3 variables, not 2. Right? Well, that gives me the gradient of, oh, look, a bonus comma. That one was free. Doesn't belong there. I never have students make this mistake. I've seen many other mistakes. This is the mistake I have yet to see. For the Elijah component. I don't know what that means, but okay. It's a Jewish tradition. Yes, very nice, very nice. I get it now. I don't have a lot of Seder-based calculus humor, but I'll take it. Let's see here. So x hat, y hat, z hat. Look at this. The gradient vector fields of y, x, y, and z in 3 dimensions are exactly x hat, y hat, and z hat. The picture, I love these pictures. So this we're looking at is these are constant x, right? X equal to 1, x equal to 2, x equal to 3. These gives you vertical planes where y and z are free to vary, but x is stuck, frozen. The normal to those planes is exactly x hat. Over here, we've got, I think, y fixed, right? So x and z are free to vary, and y hat points direction normal to the plane. And, of course, I got to have z. So z hat, the horizontal planes, right? Up is z hat. And then, of course, I have to put them together. And so what you have here is what you can imagine is this grid of x, y, z coordinates, right? It chops up 3 dimensions into these little blocks. And you can figure out where you are based on which block you fit in, right? And it gives us this sort of orthogonal grid that fills space. This is the x, y, z coordinates system. You're like, what about other coordinate systems? Well, I'm glad you asked. So here we're looking at the r hat, just the cylindrical radius vector field, right? This guy, theta hat, wraps around the z-axis like that. The constant thetas are these half planes we've looked at before. Constant r, cylinders, thus the cylindrical coordinates. Constant z, well, those are just, again, the horizontal planes, but I drew them in a more cylindrically way. And here's all of them put together. As you can see, here's the really cool thing, guys. If you take a particular point, they form a right-handed triple in the sense that if you point your right hand in the direction of theta hat, right, and you cross it into z hat, what goes out is r hat. So in this sense, r, theta, z is a right-handed coordinate system in that order because theta hat cross z hat gives me r hat. And likewise, r hat cross theta hat gives me z hat. And you can verify that right-handed relation at any one of those pairs of these triples. Less exciting for x, y, z hat, but still true, right? X hat cross y hat, z hat everywhere. Well, yeah. And you're like, well, surely, this lecture is not complete without a discussion of spherical. Now here, I claimed you could derive these geometrically. That's a bluff. Most of you can't. I can't on certain days. But I can always calculate the partial derivatives of these rewritten as functions of x, y, z, which I might have left as an exercise and or homework. I probably should make that homework. It'd be good homework for you guys. And so here is your rho hat, the spherical unit vector field. This guy here, what are these?
Those are the theta.
Yep, this is, again, theta hat, just done in a spherically way. These guys, it's the hardest one to graph, I think, but this is the, as we called it, the colatitude, right? These pointing down like that. And if, again, here, and I didn't even try to plot the whole thing. I just plotted a particular octant, the only one I have the number for, 1. And so in the first octant, check it out. So rho, why does it have to be rho phi theta? If I do rho hat, let's just pick this point right here, right? Rho hat points out at you. Phi hat points down. Right hand, theta hat, this way. See that? Rho out, phi down, theta hat this way. And you can always check that rho hat cross phi hat gives you theta hat. That's why we have to say rho phi theta coordinate system to make it a right-handed coordinate system. But anyway, we are starting to make connections between calculus and geometry. I hope you appreciate that. I will shut up for today. Thanks, guys.